And capital R over capital R is 1, and arc sine of 1 is asking when is the angle, when do you get a y coordinate of 1? Pi over 2, right? So this is going to be r times pi over 2, and then minus, this is 0, right? Arc sine of 0 is saying where on your unit circle is your y coordinate 0, and that's going to be at 0. Why is it not pi? Domain restrictions of arc sine, right? Okay, so that's 0. So your answer is just 1/2 pi r, right? Yeah, and that was only a quarter of it, right? So multiply that times 4, and you get 2 pi r. Pretty nice, pretty nice. Okay, now, and we ate up so much time at the beginning of class. Just for the quiz score to be dropped.
We're sending
Nice,
some
nice, nice, nice. Okay, so when I started this whole topic out, I said, you know, what if we have a curve like that, right? And we want to find the length of it. And then I zoomed in on this piece, and I said, you know, let's say we're trying to find that, and then I drew a rectangle like this, triangle, sorry. And I said that this was dx and this was dy, right? So that was our construction. Well, what if this curve up here is not y equals some function of x? What if I don't have that? What if I have x as some function of y instead? Okay, what if I have that instead? Okay, so like a parabola that opens sideways, and I want to know the arc length. Make sense? Well, this doesn't change, does it? Like this is still the same, and this hypotenuse is still the square root of dx squared plus dy squared. That's still the same. But remember what I did earlier is I said this is something we can't really mess with, so we replaced the dy with taking the derivative with respect to x on both sides of that, right? So what I'm going to do now is I'm going to work with this, and I'm going to take derivative with respect to y on both sides of this one. Okay? So if I do that, I'm going to get what? Dx dy equals, well, g prime of y, right? That's the definition of the derivative of g with respect to y. And then I multiply both sides by dy. So that means that dx is equal to g prime of y dy. And then I come in here and I replace this with that, right? And so what you essentially get is this. I'm not going to go through all the details because it's exactly the same. You're going to get g prime of y plus 1, and then a dy factors out this time instead of a dx. dy comes out. So the difference in the formula is, well, is it different? No, I mean the one could go the other way, right? So the only difference here in the formula from this one to this one is that this is what you use if y is some function of x, right? And you're on some interval ab, where ab is your left and right. But if you have something where you have x is a function of y, so if x is some function of y, and you're on some interval cd, where these are y coordinates instead of x coordinates, then your formula changes only in respect that you're still going to go from c to d, right? So you're still going to go between that interval. This is still going to be 1 plus, but instead of the derivative of f, it's going to be the derivative of g, right, with respect to y. That squared dy. That's what you were referring to earlier, right? So like, you know, what if we want to work with this sort of situation as opposed to this one? We can still do it. Doesn't really change a lot. Okay? Questions? So let's look at one like this. I'll leave that up for now. That seems uninteresting. Okay, I'll just do this one. X is equal to 1/3 square root of y, and then y minus 3, and then we're going to be on the interval 1 to 9. So those are y values. So we want to find the length of this curve. So is it obvious to you that it's solved for x? So this is a function of y, right? Is that obvious? So let's call this thing, let's just call it g of y, right? So we're going to need to know the derivative. We're going to need to square it. We're going to need to add 1. We're going to take the square root. Same thing we just did, right? Everything's the same. So the derivative of this, you know what? I don't think I'm going to do the derivative yet. I think I'm going to just like multiply the square root of y through. So I get like 1/3 y to the 3/2 minus y to the 1/2. Right, that's what I would get. Just rewriting that as y to the half and then hitting this, and that adds the exponents, and then here to here, 3's cancel. It's just easier for me to take the derivative of that than it is to try and do like product rule or something. You could do product rule, but it's just, yeah. So now, derivative of this. Whoa. All right, so this comes out, that gives me a 1/2 y to the half minus 1/2 y to the negative half. Derivative, power rule. Got to square it. So we take this derivative and we square it. That should look somewhat familiar. We did problem kind of like this earlier, right? My terms here are going to be 1/4, let's see, y. That's what I get when I multiply this times this. What about my next one? Minus 1/4. And then the next one would be minus 1/4 again. And then my last one should be plus 1/4 y to the negative 1. Run that time. What did I what?
We can just do the shortcut, right?
Pardon?
The shortcut, why don't you square?
Yeah, I mean, you could. Yeah. Just make sure you get that negative in there because that minus sign, yeah. Okay, so now we have, and then we need to add 1 to this, right? So this is whatever. Let's go ahead and add 1 to it. So 1 plus the derivative of this squared should be 1/4 y plus 1/2 plus 1/4 y to the negative 1. So that these two went together to become negative 1/2, and then I added 1, so it became positive 1/2. This looks too much like the problem we already did, doesn't it? Okay, so you put that underneath the square root, you get a common denominator, things would work, things would be nice. I'm not going to take it anymore because we're almost out of time. Yes? So ... on this one. All right, now, we're going to start the next section, but we won't be able to finish it. So the next section, what we're going to do is this. We're going to, and this is the last section in terms of these geometric issues. Shit. I just realized that I've forgotten to show y'all something, but it's okay. We'll do it next class. It has nothing to do with this. I mean, well, it has to do with calculus too, but it doesn't have anything to do with what we're doing. And it'll fit in nicely if I do it separately anyway. Okay, so if we backtrack on everything, we can find the area under this. Got it. We can rotate this around the x-axis, find volume, right? We can go around different lines. We can take that thing off the page, stretch it out, measure its length so long as we can do that integral. And now what we're going to do is we're going to take this thing and we're going to wrap it around the x-axis. Okay? But instead of trying to find the volume of that solid, we're just going to imagine just this curve going through, okay? And it creates a surface. Right? So, like if you went and did this whole region around the x-axis, you'll get a solid, right? But I'm saying don't take the whole region. Just take the curve itself. Just the curve. And wrap it. And then we want this, it's basically the surface area of the outer edge of the solid. So one simple example would be if I just gave you this little short line segment, right? And I said, wrap that around the x-axis. Then you would get that, right? And I could put my hand through it and everything. And I would want to know what the surface area of that is. So if I had to paint the outside of it, I could. Understand? Okay, so how are we going to come up with that? Well, what we do is this. We imagine taking a very small little piece, okay, of this, and taking just that piece and wrapping it around the x-axis. So if I took that little piece right here, that little piece of the curve, and wrapped it around the x-axis, I would get this almost like a rubber band, right, going around this. That's not that great, but good enough, right? Just that one little slice goes around. I would get like a rubber band looking thing, right? And we want to know what the area of that is. The area, not volume. So I do what I've done before. I snip it, right? And I lay it open. So if I snip that and lay it open, it's going to look kind of like this. Oh, wow, that's bad. Okay? So we want to know the area of that rubber band that's been cut open. So how tall is this rubber band? Well, just like before, remember, if I cut this and open it, then it's the circumference, isn't it? And the circumference is 2 pi times the radius, which we just actually proved that formula. But this is going to be 2 pi, bless you, times the radius. Now, what is the radius in this particular situation? Distance from here to here, right? Which is actually distance from here to here, which is actually the function's value. That's the height of the function, isn't it? So this is going to be 2 pi times the function's height. And then how wide is it? How wide is this? And normally we would say dx, right? But the problem is that this is a curve, right? This is a curve. So we are going to not take the width to be this distance straight across. We're going to be taking the distance to be the hypotenuse. And what is the hypotenuse? Well, that's the arc length formula we just came up with, isn't it? It's the arc length formula. So this distance right here is actually the square root of 1 plus the derivative of the function squared dx. Right? That's going to give us the exact answer because dx by itself is assuming that this was truly like a flat curve. There was no curve to it, right? So that would give us, if we multiply this times this, that gives us the area of that one rubber band, right? But we want to add them all up. So we bring the integral in. So here it is. The surface area will be equal to this times this. The 2 pi is a constant, so it's going to come out. Integral goes from a to b, a here, b here. And then we'll have the function f of x, that's this, times the square root of 1 plus the derivative of f of x squared dx. And that is your second formula of the day. What's the difference between the arc length formula and the surface area formula? Not a whole lot, right? 2 pi, that's different. F of x, that's different. That's all though, right? 2 pi f of x. Otherwise, everything's the same. Right? So what I'd like to end class with in the last 4 minutes is I'd like to go to this again. And what I want is to imagine taking just this right here, and I want to take that little piece and wrap it around the x-axis and find the surface area. Now, wouldn't that be the surface area of half of a ball? Yes? It would. Okay, so otherwise, not a lot's going to change, right? This is still capital R. This is still y equals the square root of r squared minus x squared. In fact, we've done all this work, haven't we? We've done all that work already? So let's see. Our formula for the surface area should be 2 pi, integral still 0 to r, but now what we have to put in here is this, right? This needs to be in there. And if you look in your notes from just a second ago, we have this already. So this right here for us is what? It's the original function, which is the square root of r squared minus x squared, right? Times, now what did we just have in our notes for this? On the top we had what? R squared, which we took the square root of, right? And we got an r. And on the bottom, what did we have? The square root of r squared minus x squared dx. Yes? Yes? That's nice. Okay, because this is a constant, right? So this is just 2 pi capital R integral 0 to capital R of 1 dx. And if you look, and if you do this, this right here, the antiderivative from 0 to r of a constant is just this times this. So you can do it yourself, but you're just going to get r here. Okay? This part right here. You just get r. Right? So you're going to get what? 2 pi capital R times capital R, which is r squared. But that's half of it. Right? That's half of it. So the surface area of the whole thing should be 4 pi r squared, which you can check your formula sheet. That's what it is. I hope you followed that. That was really fast, but I was out of time. Okay, so we are going to come into class on Wednesday, the day before Halloween, right? And please do not let me forget, because it guaranteed it has to be on the test. We need to do volumes of cross sections, all right? So don't let me forget that on Wednesday. We need to start class with that, all right? Volumes of cross sections. Enjoy your homework. Do as much as you possibly can. We just started this, by the way. We have to look at surface area a little more. All right, we just started. There's a couple of other things we need to look at. But at least get through any homework related to 7.2, 7.3, 7.2, there's no 7.3. For 7.4, at least do 7.4. There's only 2 problems in the homework. There's only 1 problem in 7.5. What? Yeah, just make sure you're caught up with your homework. Look, try some other problems, doesn't hurt. Have a great day.
Professor,